I'm Adam from RFOXiA from our real lab. Today we're answering the question that every hardware engineer has quietly asked themselves at least once. Why did we spend so long wiring 7 separate sensor modules when one board could do all of it? Let me describe a situation you may recognize. You are building a drone or a robot or an environmental monitoring node, something that needs to know where it is in space, how it is oriented, what the air around it feels like, and whether that air is chemically doing anything interesting. Standard requirements, nothing exotic. So you start sourcing components. You need an accelerometer and a gyroscope for motion. You need a magnetometer for heading. You need a pressure sensor for altitude. You need a humidity and temperature sensor for environmental data. You need an air quality sensor because it turns out the air quality matters quite a bit if you are flying through it or reporting on it. That is 6 chips. Some of them come as combined packages, so you might get down to 5 boards, maybe 4 if you are optimistic and your order from the supplier does not arrive with one of them substituted for a package compatible but register incompatible alternative that nobody warned you about. You now have 4 to 6 breakout boards. Each one needs power, each one needs ground. Most of them use I2C, which is good because I2C is a shared bus, and theoretically you only need 2 signal lines for all of them. 2 wires, simple, except I2C requires every device on the bus to have a unique address. Addresses in I2C are 7 bits, which gives you 128 possible addresses minus the reserved ones, which leaves you somewhere around 112 usable addresses, plenty of room in theory. In practice, the accelerometer manufacturer gave their chip a fixed I2C address, not configurable. The magnetometer manufacturer gave their chip the same fixed I2C address, not configurable. You now have 2 devices that both want to be at the same address on the same bus, and I2C does not negotiate. It does not apologize. It simply stops working and gives you corrupted data that takes 3 days to diagnose because the bus does not go down cleanly. It just starts returning garbage intermittently, which is the worst possible failure mode. So you start checking address tables. Some chips let you pull an address pin high or low to select between 2 possible addresses. This helps. If both conflicting chips support this, you can resolve it. If only one does, you move the other to a software I2C bus on different GPIO pins and accept that you have now made your firmware more complicated. If neither supports address selection, you are looking at a multiplexer, a TCA 9548A or equivalent. Now you have an 8th chip which has its own I2C address and its own library and its own initialization sequence that needs to happen before any of the sensors can be addressed. And this is before we talk about voltage levels. Some sensors run at 3.3V, some are 1.8V only, some are tolerant of 5V on their I2C lines, some are not. And the datasheet will tell you this in a footnote that you will not read until after you have destroyed one. Level shifters, more components, more points of failure, more wiring. The wiring, by the way, is its own category of suffering. 7 sensors across 4 to 6 breakout boards means somewhere between 20 and 40 individual wire connections depending on how many optional interrupt pins you are using. DuPont connectors on breadboards have a failure rate that is difficult to characterize statistically because it is somewhere between annoying and catastrophic depending on when the connection fails. A loose wire during prototyping is annoying. A loose wire during a flight is a different kind of problem. And through all of this, the address conflicts, the voltage mismatches, the multiplexers, the wiring, the 6 different libraries with 6 different initialization patterns and 6 different data formats, through all of this, the actual engineering problem you came to solve has not advanced at all. You have been solving the sensor sourcing problem, the wiring problem, the address conflict problem. You have not yet written a single line of code that does what you actually needed the sensors for. This is the situation that the conventional approach produces. It is not the result of any single bad decision. It is the accumulated result of treating each sensor as an independent product rather than a system component. Each manufacturer optimized their chip in isolation. Nobody coordinated addresses, nobody agreed on voltages, nobody thought about what it would be like for the person who needed all 6 capabilities on the same bus at the same time. The Multinav Pro plus Sensors module consolidates your entire sensing stack onto one I2C line, so you spend your time building things instead of untangling a wiring disaster. Here is what that actually means in practice. All 7 sensors, accelerometer, gyroscope, magnetometer, pressure, humidity, temperature, air quality, are on 124 mm by 18 mm board. They share a single I2C bus. Each sensor has its own dedicated I2C address, selected and validated at the hardware level with no conflicts. You connect 2 signal wires, power and ground. That is your integration work. The sensors were selected not just for capability but for compatibility. The BMI 270 from Bosch for motion sensing is a professional-grade IMU used in demanding applications. It delivers the kind of update rates and noise performance that makes it useful on a moving platform rather than just in a classroom. The TMAG 5273 from Texas Instruments for magnetometry. The LPS 22HH from ST Microelectronics for pressure. The MVH 4003D from MEMS Vision for humidity and temperature. The ZMOD 4510 from Renesas for air quality. These are not the cheapest available parts, they are the right parts. So that is the architecture, why it was broken before, and how a single I2C bus with no address conflicts changes what you can actually build. Now let me show you the hardware itself. This is the complete sensing stack on one board. Accelerometer, gyroscope, magnetometer, temperature, air pressure, humidity, and air quality. 7 sensors, 1 module. The entire category of sourcing, wiring, and address conflict problems that I just described is eliminated before you write a single line of firmware. This is the division of labor. The BMI 270 handles motion, attitude, vibration, angular rate at the update speeds a drone or moving vehicle actually needs. The environmental sensors handle what the air is doing around the platform in real time. Both categories of data, one I2C transaction. These are the specific components on the board. BMI 270 from Bosch SensorTech for motion. TMAG 5273 from Texas Instruments for magnetometry. LPS 22HH from ST Microelectronics for pressure, MVH 4003D from MEMS Vision for humidity and temperature, ZMOD 4510 from Renesas for air quality, professional parts, not the cheapest available, the correct ones. One I2C line, each of the 7 sensors has its own dedicated address, resolved at the hardware level, not in your firmware, not with a multiplexer, not with the software I2C workaround on spare GPIO pins. You connect 2 signal wires and the bus works. That is the entire integration process. 24 mm by 18 mm. This is the form factor that makes it possible to mount a complete environmental and motion sensing suite on a drone arm inside a wearable enclosure or in any compact IoT node where a cluster of 6 breakout boards connected by 40 jumper wires would not physically fit. Real-time data across all 7 channels simultaneously, temperature, humidity, pressure, air quality, acceleration, angular rate, and heading, streaming from one module on one bus through one connection. You monitor, you react, you optimize. The hardware is not the bottleneck anymore. Robotics, environmental monitoring, precision agriculture, drone navigation, smart city nodes, field research, wearables, industrial IoT, any application that needed to know what a space felt like and how a platform was moving through it. This board covers the sensing requirement without the conventional integration penalty. At 24 mm by 18 mm, this module fits on a drone arm, it fits in a wearable enclosure, it fits in any compact IoT deployment where the old approach of 6 breakout boards connected by 40 jumper wires simply does not fit at all. The conventional question was, which sensors do I need and how do I wire them together? The correct question was, why am I solving a wiring problem instead of the actual problem I came here to solve? Those are different questions. The answers are different hardware.